Good morning. In the previous two lectures on stereochemistry, we talked in great depth about the concept of enantiomers. Enantiomers are stereoisomers which represent mirror images of each other. And these mirror images cannot be superimposable. So these are the cases where a molecule and its mirror image are actually different species. Today we will expand this one class of stereoisomers by talking about diastereomers, which are actually a much broader class of stereoisomers, and which, just like all other stereoisomers, differ in spatial orientations of groups, but they're not mirror images of each other. And one way to look at this is to consider all stereoisomers, which then split into two big categories. One are enantiomers, which, as I said, are mirror images of each other, and the others are diastereomers, and these are all other stereoisomers, which are not mirror images of each other. We've actually already seen a couple of classes of stereoisomers, and those are the so-called geometric isomers, also known as the cis-trans isomers. And we've seen them in alkenes, when we had the trans butene and the cis butene, and we've also seen them in cycloalkanes, when, for example, we had the trans dimethyl cyclohexane and the cis dimethyl cyclohexane. Today we will talk about diastereomers of molecules which have two or more stereocenters. And this class of diastereomers is actually intricately connected to the enantiomers, and that's why we consider them together. So in very simple terms, if we start with a molecule which had one stereocenter, and we'll draw them now in a conformation which is conveniently converted into Fischer rotation, and then simply add another stereocenter, then we'll have a molecule which has two stereocenters. Okay, and this is obvious enough. And we can convert this into a Fischer projection, which will look like this. We have H here, Br here, H here, and Cl here, and then finally Ph3 here. But if we look at if the configuration on that other stereocenter, if we keep the first stereocenter the way it was, and then invert the configuration on the other stereocenter to get something that looks like this, and then convert this into Fischer projection, what we will see is that these two molecules are not mirror images of each other. Even though the orientations of individual substituents on both of the chiral carbons are different, they're still not mirror images of each other, and therefore such classes of compounds are called diastereomers. Okay? And so we can figure out configuration on these systems relatively easily. If we now look at these two compounds, on the top carbon we'll have priorities 1, 2, and 3, and they will be oriented clockwise, but since our hydrogen is in the front, that would mean that this configuration is S. While on the bottom carbon we'll have priorities 1, 2, and 3, and they will be ordered counterclockwise, but because hydrogen is on the top, this will be R, and so this will be the SR isomer. If we look at the second molecule that we just drew, the configuration of the top carbon will be still the same as, but the one on the bottom carbon will be switched, and so this is now R. This is now S again, sorry. And so the configuration of this system is SS. And what we can notice is the SR does reflect, and we can get to an enantiomer if we just switch the configuration of both of them. So this will be an enantiomeric relationship. And the same will apply to SS switching into RR. But all the other pairs where not everything switches, but just parts of molecule, are diastereomeric. So these relationships are all diastereomeric relationships, meaning that they are different compounds, and they're different only in spatial orientation, but they're not mirror images of each other. As we see in this case with bromine and chlorine, we have a total of 4 diastereomers. And these 4 diastereomers come from 2 chiral centers. And so we can have SS, SR, RS, and RR. And we can also draw all of these. We already have 2 of them up here. But just for completeness sake, we can first switch the first carbon. And it looks like this. Then we can switch the second carbon while keeping the first constant and get something that looks like this. And then finally we can switch both carbons. Which now looks this way. And this is a general rule that if we have n stereocenters, this will lead us to the maximum of 2 to the nth stereoisomers. This is an interesting observation. So in this case, n is 2 because we have 2 stereocenters, and 2 to the second is 4 diastereoisomers. So we have 4 total of diastereoisomers, the maximum possible number. But in the next topic, we will see the cases of systems where we don't have this maximum number. We have slightly lower number of diastereomers, and we'll see what causes that to happen.